Hello friends, in this lecture I would like to explain another example based on the L-beam, that is design a L-beam for an office floor to suit the following data. So here the clear span will be given 6 meters and center to center of the supports will be 6.3 meters. The L-beam are monolithic with RC columns. Spacing of the beams will be 2.75 meters center to center. Load will be given 4 kilonewton per meter square. Thickness of the slab will be 100 mm. Width of the column will be equal to 300 mm. Use M20 grade concrete and Fe415 HOSD bars. Floor finish will be equal to 0.6 kilonewton per meter square. Plaster finish will be 0.49 kilonewton per meter. So already in the last example I explained one topic which is based on T beams, and today I will explain the topic based on L beam. So both are the flanged beams. T beam and L beam are the flanged beams. For example, what is T beam? T beam means the beam along with either side of the slab. So this is slab part and this is beam part. And what about L beam? L beam also the beam only combination of the slab, not either side. That is L beam. So it is in the shape of T and it is in the shape of L. Therefore, it will be different. That is T beam and L beam. So you see the picture what I showed in the last class for the T beam. See here. So in this building, we can clearly see that the end portion of the beam along with the combination of this half part of the slab considered as L beam. Here also this end, the beam along with the combination of the half part of the slab called as L beam. But the intermediate beams, that is beam either side of the slabs, will be considered as the T beam. So in the ground floor slab, first floor slab, second floor slab, you see the difference. There will be 6 T beams, intermediate T beams, and 6 L beams, edge beams. Like that, the T beam will be intermediate beams along with the either side of the slab, and L beams are the edge beams along with the slab. So the data also refers to the same here. Clear span of 6 meters means we are going to design one clear span of the beam, means one particular beam of some around 6 meter completely. And again, center to center of the supports means generally how the beams will be laid on the columns. So the column will be around 300 mm. So the width of the column is clearly given here. At the same time, center to center they will mention like this. So totally how much it will be around? It will be 6.3 meters. We are going to design one particular L beam which is edge beam. So if you see here in this picture, we are seeing from front view, means we are observing only L beam, T beam, L beam, but here we are designing only this edge beam from here to this back, means which is I am seeing from front view. So if you see from side views, you will get that this L beam total. Like that, we are going to design one particular L beam here, and that laid on the column width will be given. And again, so the slab will be given, slab also if you see from side views, so the slab will be around some 100 mm. Like that, they will clearly given the slab thickness will be some 100 mm. So this width of the column will laid around 300 mm. If you see here the figure, I will draw this beam from side view, front view. So again, the what is the next value they given here? Thickness of the slab. Before that, spacing of the beams will be 2.75 meters center to center. Means from this L beam to this T beam, the spacing will be 2.75 centimeter, 2.75 meters center to center. Means from this center to this center of the T beam, the spacing will be 2.75 meters. But we are designing one particular L beam from this one to this last. Okay. So see here, I will show that image also. Though this is the L beam. In the picture what I shown, this is T beam, T beam, T beam. So this is L, T, T, T. So again, if you I'm observing this one from the side view, means this will be 6 meters, and around it, the center to center of this column will be 6.3 meters. Like that, the given data will be okay. And again, what is the data given in the question? Use M20 grade concrete. F means your characteristic strength, that is FCK will be equal to 20 Newton per mm square, and Fi will be equal to 450 Newton per mm square. Then what is our first step? So you can go for the cross sectional dimensions. Each and every time our first step is finding the L by D ratio, that is cross sectional dimensions. So generally we are taking span to depth ratio based on the range of the span they will given. So while explaining the first concept, that is singly reinforced beams, so I shown the table also. So for what range we have to take the L by D ratio. For example, it will be 3 to 4 meters. We will take the span to depth ratio will be around 15 to 20. So if the span range will be, so this is span range and this is the L by D ratio value. Similarly for 5 to 10 meters, it will be around to some 12 to 15. Similarly, it will be greater than 10 meters, it will be around some 12. Like that, the ranges will be different here. Means we can take down 12 and above less than 12. That is the difference what they will given. But here, our span range will be around 6.3. Means we can choose the range between 12 to 15, or else you can take 12 also. So I will prefer the L by D ratio will be around 12. And what about your span range? So we know that we are always considering that span range will be given, center to center of the supports will be equal to D equal to L by 12. So around 6,300 divided by 12. So you will get approximately the value will be 525 mm. So I will, for maximum depth required, we will choose higher value only. So I will go with the approximation 550 mm is the effective depth what I adapt here, and again overall depth will be again based on its effective cover, removing the effective cover of some 25 mm top and bottom. So I will choose around 600 mm. So we know all these conditions. Why? Because already we solved so many problems in our channel, that is T beam, L beam, singly reinforced beam, doubly reinforced beam, cantilever beam, continuous beam. Each and every time explaining what is effective cover, what is the span to depth ratio, how we are adopting this effective depth clearly. So I think you are in the continuation only. You no need to explain briefly about this topic here. So wherever the data will be totally different for L beam, there I will focus more and more. So remaining part I will lightly explain and I will continue the problem for time's sake. So your effective overall depth will be around 600 mm. And again width of the beam also we are adopting, that is BW. So width of the column will be given, width of the beam will be 300 mm. And we know the condition, it does not greater than width of the column. So you can take that condition also. Whatever the width of the beam we are adopting here, it does not greater than width of the column. So like that I am taking the same value, which is width of the beam will be equal to 300 mm. Then after knowing this one, our next step is finding effective span. So what is the formula for effective span? For simply supported conditions, what generally we are taking? So effective span will be equal to center of the supports. That is our first condition, center to center of supports. So we know that that will be given in the question itself, which is 6.3 meters. And again is clear span plus its effective depth. So clear span will be 6 meters plus effective depth what we adopted 550 mm. So which is 0.55. So if you simplify, you will get around 6.5 meters. Adopt with this whichever is less value. So adopt whatever the lesser value you will get, you can adopt this one. So our effective span will be equal to 6.3 meters. Then our next step is finding loads. So for loads, generally for singly and doubly reinforced beam, what we are taking? So directly we are assuming that only for beam self weight, but here there is a combination of both beams and the slabs. So we will see how it will be loads. So first one will be, we are designing both beam and slab part. Okay, so this effective width will be how much? It will be around, we know the condition of, so it will be around 100 mm, and the effective depth will be given from center to, it will be 500 mm means 550 mm means So the overall depth will be 600 mm. So if you remove the slab part, only the web part will be 500 mm. Okay. So self weight of the slab. First we are taking this red part, which is slab part. Self weight of slab, that one will be equal to, we generally how we are calculating this one. So already slabs also I explained for slab part how we are taking. So this d into and again, so this range will be, slab part will be like this, up to 6 meters span. So we are considering in the lengthwise, in the 6 meters lengthwise, we are just considering 1 unit, that is 1 unit. In the widthwise, how much they are given? Center to center of the spacing will be 2.75 meters, which is center to center, means another T beam will be there. So that is also I will draw here with another mark. So this is continuation. So this is intermediate beam. So I will show you the different combinations. This is part. So the value will be around center to center of the span, means exactly from this center only. Okay. Then here, so we are exactly taking in this 2.75 half part, means center to center spacing will be exactly from center. So you remember this one, here also center, not from the end. So here we are taking only this half part, means which is at point, that is 2.75 by 2, means we are taking only half part for calculating the effective loads. Why? Because the remaining half part goes to the another beam, which is intermediate T beam. Only we are designing some simply supported case like both are T beam, means this will comes under this part. Okay, therefore we are taking just exactly half part, that is 2.75 by 2. 2.75 by 2 means here what covered? Length covered, depth covered, and also breadth half part will be covered. So we know the condition, L into B into D. L into B into D into its unit weight of the RCC. Unit weight will be equal to around some 25, which is 25 kilonewton per meter cube. So if you simplify, how much you will get? D will be around 100 mm, which is 0.1 in meters. So simplify all these values, you will get around 3.45. That too, meter and meter cube will be cancelled. We are considering this for 1 meter unit, that is kilonewton per meter. Okay, so this is how we have to calculate for the T beams, L beams. Then floor finish will be what they will given in the question, floor finish. So floor finish will be given around 0.6 kilonewton per meter square. Means what they will given? They are given along with this value, which is kilonewton per meter square. If you want in terms of kilonewton per meter, we have to add this effective width value. So I will explain that one. That is 0.6 into this half of this value, which is 2.75 by 2. So we can take exactly half of this span. So you will get around 5.50, sorry, 0.83 kilonewton per meter. And again, what is live load they are given? Live load also they are clearly mentioned that 4 kilonewton per meter square. So which is live load? That is 4 kilonewton per meter square. For that also what we have to do? We have to take down into 4 into this part, 2.75 by 2. So you will get around live load will be 5.50 kilonewton per meter, and the next value will be plaster finishes, and that value will be directly given 0.49 kilonewton per meter, not meter square. So it will be in kilonewton per meter, it will be directly given without any calculation. Okay, then after taking all these things, then this is the slab part will be completed. What are the dead loads and live loads acting on the slab, and slab part will be completed here. Then go to the next part, which is self weight of beam, which is web part. So that is, we know the conditions for this also, that is B into, that is 300 by 500 into its unit weight. So we know that one for beams generally 0.3, and after removing the slab part it will be around 0.5 only. And this beam also we are designing in the width wise, in the length wise for 1 meter. So like this, this is also in the length wise. So this is the slab part, these two, okay, 1 meter only into its unit weight. Just like how for beams we are calculating, the same way we are calculating here dead load of the beam, that one will be equal to around 3.75 kilonewton per meter. If you simplify all these values, so how much you will get here? So this one will be around 3.43. Sorry, this is not 3.45. So take down 3.43. 3.45 also no matters. And again another will be 0.6. Another one will be 0.83. Another one will be 5.50. Plaster furnishes will be 0.49. Total working load, how much it will be? If you add all these things, you will get a total working load as, that one will be equal to 14 kilonewton per meter. Then comes to the effective flange width. So our next point is effective flange width. So we know how to calculate effective flange width for T beams, already I explained in the last lecture. Similar way for L beams also there will be some formulas in the code book, which is page number 37 in IS 456. See here, 37 page number. So the conditions will be given for effective width of the flange. In the absence of more accurate determination, the effective of flange width may be taken as the following. So the condition will be, but in no case greater than the breadth of the web. So here what they are given, the breadth of the web means width of the web beam plus half sum of the clear distance to the adjacent beams. Clear distance between the adjacent beams will be given how much in our case? In our case it will be around 2450. So I will tell you how it will be. Then another condition will be for L beams, the formula will be this one. So out of these two you can take the condition whichever is less. Okay, for T beams this will be this one. So they are asking the question of intermediate beams, like this is T beam, L beam. They are asking only one L beam, design only one L beam, like this means you can take iso beam formula will be this one. But in the continuation on a particular beams, they are asking to design one particular L beam means you can prefer this formula. So there will be two conditions. I will explain both the conditions. First take down this formula. First one will be BF will be equal to L0 by 12 plus BW plus 3 times of DF. So what is L0 by W? L0 by 12 will be equal to 6300 is the effective span divided by 12 plus width of the support will be 300, which is width of the beam, plus 3 into 100, that will be around 1125 mm. So this is the first condition, and coming to the second condition I will explain that one. So BF will be equal to BF plus 0.5 into spacing between the ribs, spacing between the ribs, that is the condition what they are given. So generally what they are given in the question, spacing between the ribs from center to center will be equal to, from center to center will be equal to 2750. In this the condition is spacing between the ribs here, not center to center. So 2750 minus 2300. So if you simplify this you will get around 2450. So like that you will take BW will be equal to around 300 plus half of the 2450, 0.52450. How much it will be? It will be around 1525 in mm. So out of this we will consider whichever is lesser value. So lesser value will be this one. So therefore our effective flange width will be 1/25, 1125 in. So here in the T beams, for example, this will be a T beam. If you see here, so this is the continuation to the T beam. So the T beam will be like this. So here if the effective width of the flange will be some 1000, means for T beams exact from center to here, half of this one 500, and from center to this one half of the width. Like that, overall effective width will be taken from center to either of the supports, means flanged section. But here for L beams, if the effective width of the flange will be some 1000, means it will comes from end. So that is the major difference what you have to observe. For T beams we can take exactly from the middle of the web from either of the span, but for the L beams it will be taken from end to the remaining part. So here in our case the effective width of the flange will be around 1125 and 1525. So out of these two we are considering lesser value. So our value from this end to here is 1125 in mm. First, just for example sake only, I use this value here. Okay. Then move to the next step, that is ultimate bending moment and shear forces. Ultimate bending moment. So first comes the ultimate bending moment. So this is the L beam which shows the cantilever portion here, and these two are the support columns. So the support section of this L beam which shows the supports along with the L beam. The support section of the L beam is the most critical section. So here at the support there will be torsion moment, bending moment, and shear force also acting. If you observe very clearly the supports of section which includes on the column, so there will be torsion moments, bending moments, and shear forces. So torsion and hogging bending moments are maximum in the vicinity of the column supports, where the L beam is built into the column, while the sagging moments are maximum at the center of the span. So here the support section of the L beam is the most critical section designed for combined torsion and shear forces according to the IS 456. So while solving the bending moments, we have to take care maximum center of the span there will be only maximum sagging moments are developed at the center of the span, and at the support sections there will be torsion moments, bending moments, and also shear forces. First we can see at support section and then middle of the section. So at support section what is the bending moment here? So at support section, so generally at fixed support it will be like this. The bending moment at support section will be so see here. So the bending moment at support will be WL square by 12. We know that one. And maximum at the center of the span will be WL square by 24. So here also. And what about the shear forces? The shear force will be like this. For fixed support, the conditions will be the shear force will be like this, which is WL by 2 on both sides. So this is WL by 2. So the shear force will be, here also it will be WL by 2. So either supports it will be WL square by 12. So we learn all these things in the basic strength of materials, and at the center it will be WL square by 24. So therefore at the support section the value will be around WL square by 12. So how much it will be? So it will be 14 into, so total overall load will be 14. L is 6.3 square by 12. For simply supported case it will be WL square by 8 only, but for the fixed support conditions the values will be, so it will be around how much, just, so it will be around 46.305. So we can calculate safety factor. So ultimate load, ultimate moment will be, mu, which is taking factor of safety, that is 1.5. Simplify this one, you will get around 70 kilonewton meter. Similarly, at center of this span, how much it will be? So the moment will be equal to WL square by 24. So take down factor of safety including here. So simplify, 1.5 into 14 is the load, that is ultimate load. So we are calculating just total load, that is not ultimate, and 6.3 whole square by 24. If you simplify this one, you will get around, this one will be 35 kilonewton meter. So the bending moment at support section will be higher comparing to the center, and at the same time next step is shear force. So what is shear at the support? Calculate here itself, that is 14 into the length of this span will be around 6.3 by 2. So take down for this also 1.5 times, which is factor of safety. So the value will be around 66 kilonewton. So at support section the moment will be 70 kilonewton meter and shear will be 66 kilonewton, and center it will be 0 for the center of the span, shear will be, and moment will be 35 kilonewton meter. Then already I told you, for the L beams both torsional, for the L beams there will be torsional moments also producing. So next we are calculating torsional moments at support section. Torsion moment at support section. So here I, torsion moments are produced due to dead load of slab and live load on. See here. So these torsional moments are produced at the dead load of, from the dead load of the slab and live load on it. So therefore, while calculating torsion moment, consider only torsion moment values. See here, what is torsion moment? I am telling that this is produced only from the dead load of the slab, including its live load and live load on it. So for that, just take down the loads of the slabs. What are the loads of the slabs? So here already we calculated, this is slab load along with the floor finish. So without beam, you are calculating the torsion moment, means just slab live load and dead load. So overall load will be 14, remaining value minus 3.75. How much it will be? It will be 10.37, 10.25. So here what I am doing means I am removing just to web part. Why? Because torsional moments are produced only on the slab. So therefore it will be around 25 kilonewton per meter. So take down the value here. So the torsion moments, the overall load, how much it will be? 10.25 kilonewton per meter. So if you take down this ultimate load, it will be 1.5 times of 10.25, and again this will be taken for 1 unit meter, that is kilonewton per meter. So this will be taken for kilonewton per meter. So we are taking in terms of force in terms of kilonewton, we know that one. So if you want, this one will be in kilonewton means, so what I am telling here means on the entire slab, so this is the flange, so it will be around, what I am telling, while calculating of this plan, we are taking in the overall 6.3 meters for 1 unit, means we are considering for entire this per meter force into the entire span. For that, what we are doing, 1.5 into 10.25 into 6.3. So whenever, while doing the calculations to the overall load, you will get directly in terms of kilonewton. So if you simplify this one, how much you will get? It will be around 97 kilonewton. So while calculating the dead load and live load, just we are considering only for 1 meter. After that, the force will be considered for total span, means just we are multiplying with the total value. Then, so total ultimate shear force will be same. So that will be generally, ultimate shear will be how much here? Whatever the value obtaining here. So we know the condition. So we are taking total force is 97 kilonewton. But what is at the support? So at the support it will be distributed equally, that is 97 by 2. Here also 97 by 2. We know the condition. So whatever the load acting on the beam in terms of forces, so it will be distributed equally to its supports. So therefore it will be 97 by 2, around how much it will be? 48.5 kilonewton load will be acting, that is the shear force will be 48.5 kilonewton. Then our next step is to find the distance of centroid of shear force from the center line of beam. So see here, so this is the beam part, and again this is the slab part. This is the slab part. See here, so the effective width will be taken from the edge. Already I told you the reason why. For, and here the slab is continuous. Okay, so this is also somewhat continuous. And at the same time, we know the width of the beam will be 300 mm. And again, so always take down the reference line will be center of the web only. So center of the beam. Okay, and again, see here, distance of centroid. I want to calculate this one. Distance of centroid of shear force from the center line of beam. From the center line of. So here the effective width of the flange will be 1125, and here this one will be 300 meter, that is width of the web, and the shear force will be 48.5 kilonewton. It will be acting somewhere. So we have to find that distance from where it will be acting from the center line. Okay, this is the shear force which is acting with 48.5 kilonewton. So here for calculating this one, just we have to divide this overall slab by 2, 1125 by 2. So you will get around 562.5. So the value will be taken from here to exactly middle of the slab. Okay, exactly middle of the slab somewhere. And again we have to deduct this value. Okay, we have to deduct this value, that is 150, which is minus 150. So that 150 if you deduct means you will get 412.5, means you have to keep this Shear force value from the center of the line will be around 14.25 in meters, okay, which is, sorry, in mm, it will be around 0.4125 in mm. So this one will be around in mm. So it will be 412.5 mm from the center of the beam. Okay, then total torsional movement will be taking this force into distance. So that is total torsional moment Tu will be equal to 48.5 into its distance 412.5 in mm. So how much you will get kilonewton in terms of, it will be in terms of mm, take down in meters. So we want the value in terms of meter. So how much it will be? So it will be around 20 kilonewton meter. So the torsional moment producing from the support section will be around 20 kilonewton meter. So after obtaining this one, then our next step is finding equivalent bending moment and shear force. So our next step is to find out equivalent bending moment and shear force. Generally, while solving singly reinforced beam and doubly reinforced beams, just we calculating the maximum bending moment, and for that we have to provide the area of the tension reinforcement. But for coming to the flange beams like L beam, we have to check the moments based on the equivalent bending moment and shear forces also. So for that there will be some conditions given in code book, which was in page number 75. See here, longitudinal reinforcement. The longitudinal reinforcement shall be designed to resist a equivalent bending moment that is given by. So generally the reinforcement is for torsion, so which is given clearly in code book page number 75. So see the formula, that is mu1 will be equal to mu plus mt. So take down the same formula in the code book, that is mu1 will be equal to me1 will be equal to mu plus mt. So what is mu? So we know, again for finding this mu and mt, they will be given some conditions. So mt will be, the formula will be around, see here, this mu will be 70. So at the support section it will be critical. Therefore already at the support section we got the value around 70 kilonewton meter, and at the midspan section we got around the value of 35 kilonewton meter. First we are choosing the conditions for the higher moment. Okay, then what about this mt? So this mt, the formula will be, again check in the code book. So what is given? Tu into 1 plus d by b by 1.7. So take down the same formula for mt. So this mt will be equal to Tu into 1 plus d by b by 1.7. So what is torsion moment here? That will be 20, and again 1 plus. So what about d? So the overall depth value will be, depth of the beam will be 600 in mm. So therefore here we are taking 600, and what about b? Width of the web will be 300 by 1.7. So if you simplify this value, how much you will get? This value will be around 35.3 kilonewton per meter. Substitute the same value here, 70 plus 35.3. So the overall value will be 1.53 kilonewton meter. So this is equivalent bending moment. Then we have to calculate equivalent shear force, which was given in the code book. Around the will be this one only, same page number. VA will be equal to VU plus 1.6 TU by B. So take down the same formula, that is VU plus 1.6 TU by B. So therefore again VU will be equal to, what is the shear force obtained at the support section? It will be 66. plus 1.6, tau v will be equal to 20 kilonewton meter by b will be around, so I am taking in terms of meters, which is 300 mm, that is 0.3 meters. So overall value in terms of kilonewton will be 173. So equivalent shear force will be 173 kilonewton and equivalent moment will be 105.3 kilonewton meter. Then see here, I am telling one more condition. We have to check the same equivalent moment at the center of the span. Means, for example, for 35 kilonewton meter also I have to check like this only. But what I am doing here means I am taking the higher moment. For that I am providing the area of the steel. If possible, the same area of the steel whatever I am providing at the critical section, the same will be provided for the lower sections also. For example, you have to check the area of the steel for both the moments, but if you want you can provide individually what is the area of the steel obtaining at mid span and then at the supports. But for designing higher moment, the same area will be, means the same steel will be provided in the entire beam is also safe inside. Okay, so already I explained this logic in continuous beam. For example, at the in the continuous beams also we are providing reinforcement in the middle as well as at the support sections. There also we did the same thing. Okay, see here, providing main longitudinal reinforcement. So for providing main longitudinal reinforcement, so what is the general formula? First check the mu limit. That one will be equal to 0.138 FCK BD square. So if you simplify this value, how much you will get? 0.138. FCK will be 20 Newton per mm square. B value will be 300. D value will be effective depth value 550 whole square. We know that one. Into 10 to the power of minus 6, the round value will be kilonewton meter. If you simplify, you will get around 250 kilonewton meter. So based on this, your equivalent bending moment value will be less than mu limiting. So therefore, if your mu will be less than mu limit, we have to design the section based on the under reinforced section. We know that condition already. We are seeing so many problems based on this condition. Already I also explained in the channel based on the under reinforced section and over reinforced section. So this is under reinforced section, not reinforcement. This is under reinforced section. So based on the condition, XU also less than XU limit. So we know that one. Then provide the steel. So we know the formula which was in page number 96 in the code book IS 456. We are regularly using this formula. So I will show once again the same formula here, which was in 96. Mu will be equal to 0.87 F5. See here, the formula is this one in page number 96, annexure 38.1. That is mu will be equal to 0.87 FIAST. So I am using the same formula here also for finding area of the steel. That is mu1 equal to 0.87 Fi area of the steel into D, again 1 minus Fi area of the steel by FCK B into D. So here why I am taking mu1? Because I am taking lesser value, because this is under reinforced section. Just I am checking the moment with the limiting moment. Okay. Then we know the values. So what is mu1? 105.3 into 10 to the power of 6 equal to 0.87 into 415 area of the steel. So effective depth value will be 550. 1 minus Fi will be 415 into area of the steel by FCK will be 20. What about B? B will be 300 in mm, D will be 550. So simplified, so you will get area of the steel around 572 mm square. So after obtaining this area of the steel, again you can check the area of the steel based on the minimum reinforcement. So check with the area of the steel minimum. So that's also in the code book, the formula will be. So I'm taking here directly. So check the formula in the code. So check how much the area of the reinforcement minimum. So we know BW will be around 300 in mm, D value around 500 in mm, and Fi will be 415. If you simplify this one, you will get around 338 mm square. So the minimum area required on this T-beam will be 338, but we are providing more than this. So therefore, your area of the steel minimum will be lesser than what we are providing. So we have to provide this one only, no problem. Then again, go to the next one, then provide number of bars. So number of bars will be equal to, so we know the formula already, we solved based on this formula number of times, that is capital AST by small ast. Entire procedure remains same for T beam, L beam, all the other beams. So the capital AST what required is 572. So I will check with the dia of around 20 meter first time. So if you simplify this one, you will get the bars around 1.82, approximately 2. So check the area of the steel with these two bars, 2 into pi 20 square by 4. So it will be around 572 mm square. So sorry, 628 mm square. So this is the area what is obtained based on the 20 dia. So this area will be higher than this one, means whatever we want to provide will be higher than the obtained. Okay, therefore provide 2 bars of 20 dia at the support sections. So what I am telling means, so we provided for this moment, that is 70 kilonewton meter, and there will be which is at the support section, and at the same time we have to calculate the critical span section also like this, but this moment is higher than this one. So the same area we have to provide at the middle span also, it will be okay. So therefore I am providing both at mid span and at the support section the same area. Okay, mid span also. So for time being I am doing like this. So if you want economical, you can calculate this one, we have to provide individually also, no problem, the procedure will be same. Maybe you will get the diameter somewhat lesser bars, 2 bars of 16 dia also. Okay, then at the same time you please check the moment whatever we provided with the area of the steel. So both will be higher only, I think, therefore it will be possible. So we can provide 620 mm square, means 2 bars of 20 mm diameter only. So area of the minimum steel will be 338 mm square. So you can check with that condition while solving with 35 kilonewton meter. Again, maybe you will get around here 200 kilonewton meter, means you please prefer this one, don't prefer this one. If you want to provide this one, means it will be okay for both support section and mid span. But while solving individually, so if you will get 200 kilonewton meter, sorry, the area of the steel will be around some 200 mm square, means at that time you prefer minimum area of the steel, not this one. Okay, also you have to check this condition each and every time. And next to go to the, so this is longitudinal reinforcement is completed. Next to go to the side face reinforcement. So what is side face reinforcement? Already in the previous problem we provided only dia bars, 2 will be top and 2 will be bottom, either in tension or in compression, like this, like this. But we are not at all provided any beam at the middle. So side face reinforcement means the beams also provide at the middle like this. So why means, as per Indian standard code, if the depth will be exceeds, as per Indian standards, if the effective depth exceeds 450 mm, at that time you have to prefer this side reinforcement. So where is this condition? We will look into the page number 48. So I will show here. So this one will be around page number. So I will go with some page number 48. You see the condition how it will be, where it will be given. So where is that condition? See here, longitudinal reinforcement shall be placed as close is practical to the cover. So here, so see here, longitudinal reinforcement shall be placed as close as is practicable to the corners of the cross section, and in all cases there shall be at least one longitudinal bar in each corner of the die. When the cross sectional dimension of the member exceeds 450 mm, additionally longitudinal bars shall be provided to satisfy the requirements of minimum reinforcement, and spacing given is 26.5.1.3. So the spacing will be taken as it is like this only, but whenever the depth exceeds 450 mm, they are given the cross sectional dimension means overall depth only. So cross sectional depth diameter, so the depth will be exceeds 450 mm means here in our case the overall depth will be around 600 mm. So therefore providing side reinforcement is also must. For that, what is the procedure? That is very simple. So area of reinforcement will be taken, that is 0.1% of the cross sectional area. 0.1% of the cross sectional area. So 0.1% means, so whatever the value you are taking, so 300 by 600 is the cross section of that area. In that we are taking 0.1% means 1 by 100. So totally it will be 180 mm square. So we have to provide this much of area of the steel for the side reinforcement. So what they are telling, minimum 1 bar we have to provide for the side reinforcement. But here I will go with again some trial values, n bars. N number of bar will be equal to this capital AST by small AST. I will check with minimum bar we are using will be 8 dia only in the HYSD FE415. I will check with that bar. So it will be around 3.58. So approximately 4. So if I will check with the 4 bars, it will reach whether 180 or not. So it will be around it will be around 200 mm square. So whatever the area of the steel obtained will be lesser than the provided. Therefore, provide 4 bars of 8 dia for the side reinforcement. So these 2 bars and these 2 bars. So if you want to check with some 12 dia bar or 20 dia bar, you will get area around 200 mm square means you just provide only 1 bar exactly at the middle of this reinforcement. So the spacing whenever you are taking this one like this means, so again while calculating the stirrups, the spacing of each bars will be find out. At the time I will explain the spacing also. So this is how the area of the side reinforcement will be calculated. Then provide shear reinforcement. So shear reinforcement is also different for L beams and other beams. So what is the first step? First step is, see here in the code book page number 72. So I will show you that one around 8. Here nominal shear stress. For each and every time we have to make use of this formula only, that is tau v will be equal to Vu by Bd. Vu by Bd. So what is Vu here? Already we calculated equivalent shear force, that is around 173 kilonewton. So I will take in terms of Newton, and B in the sense BW, width of the web 300, into D in the sense effective depth, which is 550. If you simplify this one, it will be around 1.05 Newton per mm square. And again next one will be tau c. So for calculation of the tau c, we required percentage of steel. So the formula will be, which was in page number, next page. So this one 100 AST by BW into D. Again same formula for calculation of the tau c. See here, it will be 100 AST by BW into D. So 100, how much area of the steel we are taking here? Provided will be 628. Effective at the same will be 300, and again it will be 550. If you simplify, you will get around 0.38 percentage of steel. Again check with this condition for M20 grade concrete. For M20 grade concrete, so the value will be around, so check here, 0.38 will be lies between 0.25 and 0.50. So I already shown so many problems, previous examples, how to calculate this interpolation. So whatever the value lies, it will be in between. So you can use the same formula for finding interpolation. So I will use direct value in between these two. It is around tau c will be equal to. So this procedure will be same like as previous problems. You just refer the previous problem once. That is tau c will be equal to 0.42 Newton per mm square. So see this condition, it will be tau v greater than tau c here. And again check with tau c. So what is the tau c? We know the condition for tau c maximum. So I am talking about the tau c max here. Tau c maximum. So for that one, the tau c maximum will be around 2.8. We know the value directly also. Why? Because we solve so many problems for tau c maximum also. That is 2.8. So what is the condition here? So here this will be 2.8. This will be 1.05. This will be 0.42. Here it will be tau v will be greater than 0.42 and less than 2.8. So your condition lies will be second. So already tau v will be less than tau c maximum, provide minimum shear reinforcement. Tau v will be greater than tau c maximum and less than tau c maximum. Tau v will be greater than tau c and less than tau c maximum means it is second condition. Provide shear reinforcement as per IS 456-2000. If tau v will be greater than tau c maximum, you can go for redesign. Already I explained all these conditions in the previous examples also. Then here we are in the second case. Then we can provide the shear reinforcement, but it is somewhat different for the L beams. So for that you can check the code. Page number is around only this one only. See where it will be. See here this formula, which was in page number 75. So for finding SV values, we can make use of these two formulas. See here, transfer reinforcement. Two-legged closed stirrups, hoops enclosing the corner longitudinal bars shall have an area of cross section ASV given by. So take down the two formulas as it is, whatever given in the code book. So the two formulas will be around ASV will be equal to TU into SV by B1 into D into 0.87 into Fy plus, and again VE into SV by 2.5 times of D into 0.87 into Fy. So check the formula whether, once again, TUSV B1 D1 0.87 Fy plus VUSV by 2.5 D1 0.87 Fy. Sorry, this one will be B1 D1. So here simplify this one. So what is tau v here? 20. So SV is the unknown which is providing stirrups. And what about this B1 D1? See here, B1 center to center distance between corner bars in the direction of the width. Center to center distance between corner bars. So this will be related to like this. I will show here. So I will see here, your B1 will be, so we know effective width B equal to 300 mm. So B1 will be taken from the center to center, that is 250, the center to center of the bar, and your effective depth will be taken from bottom to top will be equal to D will be equal to 550 mm. But from the center to center, how much you will get? That is D1. The D1 will be around. So remove the top cover, then you will get directly the value will be 500 mm. Again I am removing some 50 mm which is top cover, that is 500 mm. So substitute the values here. Tu by see here, this B1 will be 250 here, and D1 will be 500. Similarly 0.87 into Fi will be 415, and again this value VE1 will be 170 into 10 to the power of 3. So it will be in terms of Newton. So here also you change this 20 into 10 to the power of 6 into SV. So 2.5 into 500 into 0.87 into 415. So simplify this one. So maybe you will get how many times of SV? It will be around 0.816 times of SV. So simplify one. Whatever the value obtained you put that one value. And this ASV. So generally while calculating of the spacing, so we have to prefer two-legged stirrups. So already that thing also mentioned clearly in the code book. See here, the longitudinal reinforcement shall be designed based on this. At the same time, two-legged closed hoops enclosing the corner longitudinal bars. And that too, we are seeing that preferring 10 dia. So therefore, I will check with this condition. 2 into two-legged 10 dia bars, pi d square by 4 equal to 0.816 SV. So what is 2 into pi d square by 4? So this value will be around 157 mm square. So providing 10 diameter legged stirrups, so the area will be around this one will be 157 mm square equal to 0.816 SV. So your spacing of stirrups will be equal to SV will be equal to approximately around 200 mm. So this is based on one formula. So again there will be one more formula in our code book, that is second formula. See this one, tau VE minus tau C and again B into SV by 0.87 Fi. Take down the same formula as it is, that one will be tau VE minus tau C into B into SV by 0.87 Fi, that is ASV will be equal to. So if you check with this condition, what it will be? Tau VE minus tau C B into SV by 0.87 Fi. Okay, and again substitute the same values whatever obtained here. Tau VE will be equal to, so what is the value? So we know tau V will be equal to 1.05. minus tau c will be equal to 0.42 into, again 2-legged 10 mm diameter strips will be 1.57. Take down same values, 0.87 into 415 into B into SV. So this B is generally the overall width, not B1. So we are finding this SV here. If you simplify, you will get SV value will be equal to around 300 mm. So by using this formula, you will get SV will be equal to 300 mm. By using above formula, you will get SV will be equal to approximately some 200 mm. And again, along with this, we have to check other conditions also. As per in IS 456 class 26.5.1.7, C will be, so it will be around in page number 48. So I will check with that page number. See here, 26.5.1.7. Distributed torsion reinforcement. The transfer reinforcement for torsion shall be rectangular closed stirrups placed perpendicular to the axis of the member. The spacing of the stirrup shall not exceed the least of the following. One will be x1, another one will be x1 plus y1 by 4, and third one will be 300 mm. So check along with these conditions. Already we provided, we check with these two conditions. Along with this, one will be x1, another one will be x1 plus y1 by 4, another one will be 300 mm. So what is this x1 and what is this x1 plus y1 by 4? See here, this x1 will be taken from, so here we are providing stirrups. Stirrups in the sense, these are the bars main reinforcement what we provided. Stirrups in the sense, it will be like this. So we are providing the bars, two legs along to enclose the stirrups. So this diameter bar will be around 10 mm. So we know that one will be 10 mm. So on these bars what we provided 20 mm. So if you observe here, the center of this bar to here will be 250. If you take this round bar edge, what happens? 250 plus. So it will be, I will show the same bar in the bottom. So from here to here, from the center to center, we are taking this one will be 250, which is B1. So if you take outer edge of this bar to outer edge of this bar, so the diameter will be around some 20. So plus 10 we are adding 250 plus 10 how much it will be? It will be around 280. Okay, so it will be around some 270. And again there will be one more stirrup taking here. So this stirrup center, this is 10 diameter bar, this stirrup center and this stirrup center exactly. So add plus 5, here plus 5 is here plus 5. Total it will be 280. So means what I am telling means center to center of the stirrups, that is xy, x1. Center to center of the stirrups is x1. So therefore the x1 is center to center of stirrups. So take down that as 280 mm. And again, what about x1? Same value, which is 280 mm. And what about y1? Same center to center of the stirrup in the vertical range. So here this d1 will be 500. And again for that 500 you can add plus 10 bottom dia and top dia, which is plus 20, and again plus 5 bottom and top dia, which is around you will get 530. So this one will be 530. So I will write here only, don't be confused. This is 530 by 4. If you simplify, you will get around that one will be equal to 202 mm. So third one will be 300 mm. So there will be various conditions for providing this spacing. Out of all these, we have to provide minimum, whichever is less. See here, one will be 200 mm, another will be 300 mm, another will be 280, another will be 202 mm. So out of these, provide minimum spacing, provide 2 bars of 10 mm diameter stirrups at a spacing of 200 mm center to center. So after obtaining this one, already I told you while explaining the side reinforcement, even for side reinforcement also you can provide 200 mm distance. So that is fine enough. Okay. Then, so this is how the procedure for finding shear reinforcement. So in the next step, I will show you the deflection check. So next step is deflection check, check for deflection. So this deflection also same for L beam, T beam, all other beams. So we know the condition L by D provided less than L by D maximum. So what is L by D maximum value? That is L by D basic into KT, KC, KF. So what is L by D basic? For simply supported cases, what generally we are taking? For continuous beams 26, simply supported cases 20 and cantilever 7. So I am taking 20 here. For calculation of the tension reinforcement, we know we are regularly calculating based on this formula only. So the curves will be as in the page number 39 in IS 456. See here in page number 39, there will be one curve. So first simplify this curve. Fs will be equal to 0.58 Fy. So that one F1 will be equal to 415. Area of the cross section of steel required. So in the support section and at the same time midspan section we provided 628 mm only. So the required area of the steel will be 7. So simplify with this formula 527 by 628 mm. So you will get Fs curve around 19. So where 219 curve lies? 219 curve lies between 190 and 240. So I am drawing with some reference line like this. And again percentage of steel reinforcement will be equal to, so the formula will be already we know we calculated for reinforcement also, that is 100 ASC by BWD. So generally we are taking this one will be, so we are taking only one reinforcement which is 628 only. So check with that condition only. 628 by BW into D will be equal to 300 width of the web into 550 effective depth. You will get around some 0.38. 0.3. So where 0.3 lies? 0.2 to 0.3. So 38 is approximately equal to 4 only. So otherwise you can check somewhere here 0.38. If you see the same reference line where 0.38 or keep a long scale here where the curve meets, it will be around some 1.6. So I will take some approximation like 1.7 like that here. So your KT value will be 1.7. If you want you can take 1.6 also, no problem. So based on the visibility, so here it will be KT value will be 1.7. And what about KC? Next check with compression reinforcement. This compression reinforcement already percentage will be given 0.38. If we see here exactly we will get 1.1. Why? Because we are providing reinforcement both at support section and at midspan section. Therefore, if you want you can take Kc value also. Then coming to the flange section. Flange for L beam we know there will be flange also. So for that how we have to check means, see the ratio of web width to flange width. So means BW to BF. So what is web width here? Web width is around 300 mm. So flange width will be calculated. That one will be 1125. So see this one will be 0.666. And how it will be 0.2, 0.6 means this is some 0.3 up to here. It will lies below this value only. It will be around 0.8. So that is 0.8. If you simplify, you will get the value around 29. Okay, and what about L by D provided? So this is effective span will be 6300 and effective depth will be 550. If you check this one, the value is around 11.45. Means whatever the depth, so whatever L by D ratio we provided will be less than what is the basic value. So what is the maximum chance of providing in this problem? So your deflection is also safe here. Then go to the reinforcement details. So reinforcement will be like this. So what is the beam we provided? This will be, so we have provided the bar, top two bars. So I'm giving some rough approximations. Again, so this is the stirrup providing with violet color. So you draw these bars exactly touching the surroundings. And again, this one also touches to the edge. Okay. Then side reinforcements will be like this. So we know the values. This will be around some 500 mm, 300 mm. Effective B1 will be equal to some 250 mm. So overall depth will be equal to 600 mm. So effective depth will be equal to, taken from the center of the bar to the top, will be equal to some 50 mm, 550 mm. And again, we know we provided top two bars of 20 dia. Similarly, in the bottom also we provided two bars of 20 dia. For side face reinforcement, we provided 4 bars of 8 dia. So these are the detailing of the reinforcement. And again, this is front view. If you see the same from the side view, so the bar, so this bar will be visibility in the side view like this. So I will take the top and bottom bars. The visibility will be shows like this. So stick with the same reference line in the same line like this. So it will be here. So check with the same reference lines, the same line and the same height and width also. So like that you have to place that one. And again, so this is the beam portion. And again, the violet color bars will be the stirrups. So the main longitudinal bars will be visible like this. Top bar will be like this and bottom bar will be like this. Okay, and the stirrups which was in violet color will be like this. Which is 200 mm spacing. So these are the straight bars, take straight only. So like this continuous again here also with the default spacing of 200 mm, and it will taking support with the RC column which is continuous here. and again there will be, this is flange width, so the flange of the beam, the slab portion will be also continuous like this here. Okay, we are calculated that part also including this one. So if you see from side view, beam along with the slab, and again main reinforcement bars, stirrups, and this will be cover. So if you want, you can also provide the stirrups of some bars of 2 bars of 20 dia with a spacing of 200 mm center to center, and again bottom will be 2 bars of 20 dia. So the stirrups will be 2 bars of 10 dia only. So top and bottom reinforcement will be 2 bars of 20 dia. So like that, provide width, depth, all these things. This is how we have to draw the reinforcement for L beams also. Thank you so much for watching this video. If you really like this video, please like this video, share it to your friends, and subscribe our channel. Thank you so much.